Hello everyone, welcome to this session. So in this session, we will focus on the nonlinear SVM. In the previous two sessions, we have learned the linear SVM of the hard margin and the soft margin. However, a critical limitation of the linear SVM is that the linear classifier has assumption that the data must be linearly separable. So this has very limited representation power. So because in the real world, most of the data are nonlinear, right? And linear separation, we can't solve nonlinear classification problems. So for example, with this distribution, as you can see, no matter how we draw the line to divide it, hard margin or soft margin, there's no way to separate the two classes. So in this case, how can SVM do? So there is a good news. So when we use a technique, we call it a kernel tree. So we can transfer it to a higher dimension. So then SVM can solve these highly nonlinear classification problems. So how does it work? So I'll show you now. First concept is a kernel. So the kernel, these are functions that transform data to some required forms. So normally we observe that in lower dimension, the data may be highly nonlinear. But when we map it go to the higher dimension, it becomes linearly separable. So then we first map the data to higher dimensions. So in this space, we have the linear patterns. Then we can use a linear classifier in the new input space, or we call it feature space, right? Then the problem is solved. So kernels map the input space to the feature space. The feature space is a new input space. The input space is that the data originally exists, and the feature space, as I have said, that's a transformed space. Often this is higher dimensionality, and in this space, the data is linearly separable, right? So now I give you an example. So when we consider one-dimensional case, we want to classify the red point and the blue point. So clearly by linear classifier, this can be done, right? Then we can do a feature mapping. We map it to a feature space, to two-dimensional. We can see we just fold it here, like this. So for this one, we can easily use a plane to separate the two kinds of points, right? So the data, the feature mapping, we can follow this formula. The first one is x, the second is x squared, right? So we can see by applying this feature mapping to this one, we make it to this shape, and this shape we can easily separate it by a hyperplane, right? Okay. Another example, the input space, this time is two-dimensional, is here. So we can see the highly nonlinear, right? Then we do some feature mapping. We make it to the three-dimensional. It becomes here. So then we can use a hyperplane to separate it. So in this case, the feature mapping is this one. We use this formula to transform two-dimensional data to three-dimensional data. And then in three-dimensional, this is linearly separable, right? So this is that we use kernel functions. After knowing this, we need to apply it to the optimization problem that we have solved when we use a hard margin or soft margin SVM. So let's see how to do that. So the dual problem that we have solved before, I think you have remembered this one in the last session. This is a soft margin one. We will solve this dual problem. Then we do a nonlinear mapping. We put xi, xj, we using the transform function phi to go to the feature space, right? But then the xi dot product xj, so the phi will be applied to each of them, and then perform the dot product. So phi is a mapping function. So now we can see, for example, the case we have just shown. The x space, we put phi into the z space, two-dimensional to three-dimensional, right? So if using this, we can apply this transform to xi, xj, and the dot product. We can see what is this. So phi xi is here using this mapping. Phi xj is here using this mapping. And then we want the phi xj multiply phi xi multiply phi xj, the dot product of them, and we can calculate this one. This is the result. This is the result. So it means we can calculate it, right? So with the mapping function and the new dual problem for nonlinear SVM, clearly we can solve this problem. But to solve this problem, we indeed need some effort. So first of all, for each data point in x, xi, xj, etc., in the input space, we need to apply the transformation function, the mapping function, phi x. So, and also for each pair of the data, the dot products needs to be calculated. And often the dimension of the feature space is much higher than the input space in reality. So in this way, this involves a lot of computation. So a lot of time and memory are consumed. So we want to make this problem solved more efficiently, right? So then how to solve them? There is a method. So we call it the kernel trick to help us to avoid the inefficient calculation problem. So the kernel trick, we can say we can find a kernel function. This function is a kxi, takes 2 points in the input space, not the feature space, in the input space. But however, by applying this function, we can have the dot product of their mappings in the feature space. Yeah, and in some conditions, we guarantee there exists such a kernel function. So this makes things become interesting. So let's see for kernel function, if we have a kernel function, we just apply it, and we apply the transform function, right? The mapping function to the two of them and to the dot product, and the result is the same, right? So this is tell us using the kernel trick, we can obtain this result, right? And without really using the phi, and we can using the xi and xj in the original input space, we can get the same result of this. So in this way, what we can see is that the mapping function phi doesn't even need to be defined because we don't even use it, right? And the dot product doesn't need to be computed because we can only compute here is okay, dot product here is okay. So in this way, we only need a kernel function and we can finish this complex calculation. The time saved a lot, right? So let's draw an example. So the x space is here, and the phi, we use to the z space, we use this phi, the mapping function. Then we calculate the phi xi dot product phi xj. So let's see if we don't use a kernel trick, what we can get. So phi xi is here, phi xj is here, and phi xi dot product phi xj. So we get this result, right? Now I define a kernel function. So this kernel function, we call it a quadratic kernel. So this function is considering two vector inputs, x and z. Now the result is x transpose multiply z with a square, quadratic kernel. So then we apply the quadratic kernel to xi and xj, and let's see what it happens. So we can plug it in, we can say this is the result. And we can find that this one are the same, right? So, and also we, without using this phi, we can get this result. So it doesn't matter what phi is. So in this way, the kernel trick helps us a lot to avoid this complex calculation, right? But clearly that the quadratic trick doesn't apply to all the problem, right? So there are quite some widely used kernel functions. So we can see here I listed some of them: the linear kernel, the quadratic kernel, the polynomial kernel, the reduced basis function, we call it RBF kernel, and the Gaussian kernel. So these are the formulas. Then when we have these kernel functions, we know that none of them can be applied to all the data and all the problems, right? Then there will become a problem about how to choose the appropriate kernel, right? So choosing the appropriate kernel, the appropriate kernel depends on what? Depends on the characteristics of the data and also the computing complexity, right? But we have some tips from the previous user experience. We can see that the linear kernel is mostly preferred for text classification because the data set is large. And also the Gaussian kernels or RDF kernels, they often provide good results when there's no additional information, right? So these are the experience. But however, we can also use what we have learned, right? The cross-validation to represent each kernel's performance. And then we can try them one by one and evaluate them one by one objectively and select the best one. So now we can see how to do that. So this is a cross-validation. We have go over for several times, right? So now we have the training set and the test set. The whole data set, we randomly split it to the 5 groups. So in each one, we use all the other fold as a training data, one of them as a test data, right? So this is we have I won't discuss the details because it has been described several times in the previous sessions. So now we get the training data and test data. We can apply each kernel, right? And we use different folds to see the performance of each kernel, right? So then, for example, now we have the linear kernel, we have the Gaussian kernel, we have the RDF kernel, the 3 things, right? So K-cross validation, so we can say let's say 5-fold, 5 cross validation. We got the linear kernel, Gaussian kernel, RDF kernel. Each one of them, we get 5 results. Then we can get the average of them. So this is the prediction accuracy. Then we can choose the best of them, right? So later in the MATLAB case study, you will see more details of how to select the kernels based on the cross-validation method. So here's an example that for this kind of data, clearly is nonlinear, right? So then we use a Gaussian kernel. As you can see, we can classify it quite well, right? So more details, we will see the case study later. Okay, thank you very much for listening. Bye-bye.